The story of the universe begins with an ending already written into its fabric, a strange idea that challenges everything we instinctively believe about time, existence, and permanence. When we look up at the night sky, it feels infinite and unchanging, as if the stars have always been there and will always remain. Yet, modern cosmology tells a very different story, one where everything we see is part of a vast unfolding process that began billions of years ago and will continue to evolve in ways that are both majestic and unsettling. To understand the future of the universe, we must first understand that it is not static. It is expanding, changing, aging, and slowly transforming into something profoundly different from what it is today. The universe began approximately 13.8 billion years ago in an event known as the Big Bang. This was not an explosion in space, but rather an expansion of space itself. Every point in the universe began to stretch outward, carrying energy and matter along with it. In the earliest moments, the universe was extremely hot and dense, filled with a primordial energy that eventually cooled enough to form particles, atoms, stars, and galaxies. Over immense stretches of time, gravity pulled matter together into cosmic structures, creating the galaxies and clusters we observe today. This history is important because it sets the foundation for everything that follows. The universe is not only expanding, it is also evolving, and that evolution is governed by physical laws that continue to shape its destiny. One of the most important discoveries in modern astronomy is that the universe is expanding at an accelerating rate. Galaxies are not only moving away from each other, but they are doing so faster and faster as time passes. This acceleration is driven by a mysterious force known as dark energy. We do not fully understand what dark energy is, but we know it makes up roughly 70% of the total energy content of the universe. Its presence changes everything about the future. Instead of slowing down or collapsing back in on itself, the universe is stretching outward more rapidly with each passing moment. This means that the cosmic landscape of the future will be dramatically different from the one we see today. As the universe expands, galaxies begin to drift apart. At present, galaxies are still relatively close on cosmic scales, and gravitational forces can bind groups and clusters together. However, over billions of years, these structures will begin to separate. The space between galaxies will grow so vast that light itself will struggle to bridge the distance. An observer in a distant future galaxy would see a very different night sky than we do. Instead of a universe filled with countless galaxies, they might see only their own local cluster, with everything else fading beyond the horizon of detectability. This process marks the beginning of cosmic isolation. Stars, which are the fundamental engines of light and energy in the universe, also have finite lifespans. They are born in massive clouds of gas and dust, where gravity pulls material together until nuclear fusion ignites in their cores. This fusion process converts hydrogen into helium and releases enormous amounts of energy, which is what makes stars shine. However, stars cannot burn forever. Over time, they exhaust their nuclear fuel. When this happens, their fate depends on their mass. Smaller stars like red dwarfs burn slowly, and can live for trillions of years, far longer than the current age of the universe. Larger stars, however, live fast and die young, exploding as supernovae and leaving behind dense remnants such as neutron stars or black holes. As time progresses, the birth rate of new stars will decline. The raw materials needed to form stars, mainly hydrogen gas, will gradually be used up or locked away in dead stellar remnants. Eventually, star formation will slow to a trickle and then cease altogether. The universe will enter a phase where no new stars are being born. At that point, the cosmic sky will begin to darken. Existing stars will continue to shine, but without replenishment, they will slowly burn out one by one. The brilliance of galaxies will fade, replaced by dim remnants of once vibrant stellar systems. Black holes will play a central role in this evolving universe. These objects form when massive stars collapse under their own gravity, creating regions of space where gravity is so strong that nothing, not even light, can escape. Black holes are often thought of as cosmic destroyers, but they are also silent architects of the universe. They grow by consuming gas, dust, stars, and even other black holes. Over time, many of the remaining massive objects in the universe will be absorbed into these gravitational giants. In the far future, black holes may become the dominant structures in the cosmos, outliving everything else. As galaxies age and stars disappear, they will enter what scientists call the galactic isolation era. During this phase, galaxies that were once part of clusters will drift so far apart that they become completely isolated from each other. The expansion of space will push them beyond each other's observable horizons. If intelligent observers exist in such a future galaxy, they may not even realize that other galaxies once existed. The evidence of a vast cosmic network would slowly vanish from view, leaving behind a seemingly isolated universe with no visible external structure. Inside these isolated galaxies, the remaining stars will continue their life cycles. White dwarfs, neutron stars, and black holes will dominate the stellar population. White dwarfs are the remnants of sun-like stars that have exhausted their fuel. They are extremely dense, but no longer produce energy through fusion. Neutron stars are even more extreme, composed almost entirely of tightly packed neutrons, remnants of supernova explosions. These objects will persist for incredibly long periods, slowly cooling and fading over time. They represent the quiet remnants of a once active universe. Eventually, even the most long-lived stars will fade. The universe will enter what is known as the degenerate era, a time when normal stars no longer exist and the cosmos is filled primarily with stellar remnants. In this era, matter is no longer organized into bright, glowing systems, but instead exists in a cold and dark state. Occasional interactions between objects may still occur, such as collisions between white dwarfs or gravitational interactions involving black holes, but the overall activity of the universe will be drastically reduced compared to its current state. As time continues to stretch forward, black holes will begin to dominate completely. They will slowly consume the remaining matter in their galaxies, growing larger and more massive. However, even black holes are not eternal. According to theoretical physics, they slowly lose mass through a process called Hawking radiation. This process is extremely slow, far beyond anything observable on human timescales, but over unimaginable durations, it means that black holes will eventually evaporate. As they shrink, they emit faint radiation until they disappear entirely. When the last black holes evaporate, the universe will enter a profoundly different state. There will be no stars, no galaxies, no planets, and no black holes. Only low-energy particles and radiation will remain, spread thinly across an expanding space. This marks the beginning of the dark era, a time when the universe is almost completely empty and structureless. Temperatures will approach absolute zero, and physical processes will become extremely rare. In this final phase, the universe becomes a vast, cold, and nearly empty expanse. Particles drift apart with no meaningful interactions. Time itself continues, but without change, it becomes almost meaningless in a physical sense. Some theories suggest that quantum fluctuations may still occur, potentially creating rare and random events, but these would be isolated and insignificant on cosmic scales. The universe becomes a silent and lifeless expanse, stretching infinitely outward. Yet even in this distant future, the laws of physics continue to operate. Nothing truly disappears in a philosophical sense, but everything becomes increasingly diluted and disconnected. The energy of the universe spreads so thin that no usable structure remains. It is a state of maximum entropy, where all gradients of energy have been exhausted. This is sometimes referred to as the heat death of the universe, not because it is hot, but because it represents a state where no thermodynamic work can be done. What makes this story so profound is not just its scale, but its inevitability under current scientific understanding. The same laws that govern the motion of planets, the burning of stars, and the expansion of galaxies also point toward this distant conclusion. However, it is important to remember that our understanding of the universe is still incomplete. Dark energy, dark matter, and the true nature of quantum gravity remain mysteries. It is possible that new physics could alter this destiny in ways we cannot yet predict. Still, even with uncertainty, the narrative of the universe provides a powerful perspective on our place within it. We exist in a brief and vibrant moment of cosmic history, a time when stars are shining, galaxies are forming, and complexity is abundant. This era is temporary, but it is also extraordinary. It is the only known period in the history of the universe where structures like galaxies, stars, and potentially life can exist in such richness. As we move forward in this journey through cosmic time, we will explore each stage of this transformation in greater detail. From the birth of stars to the dominance of black holes, from the expansion of space to the final fading of energy itself, the universe is a story of change on the largest possible scale. Each chapter reveals a different face of reality, each more distant and unfamiliar than the last. The journey has only just begun. The universe, as it continues its endless expansion, presents one of the most profound and unsettling truths of modern cosmology. It is not a static stage upon which events unfold, but a dynamic and evolving structure where space itself stretches, carrying galaxies, along with it. This expansion is not something happening within the universe, it is the universe itself expanding. Every point in space is moving away from every other point, not because galaxies are traveling through space in a conventional sense, but because space itself is growing between them. This subtle distinction changes everything about how we understand the future of existence. To grasp the future of the universe, it is essential to understand how this expansion behaves over time. For much of the 20th century, scientists believed that the expansion of the universe might eventually slow down due to gravity. The idea was simple. All matter in the universe exerts gravitational attraction, so over time, this force might pull everything back together, possibly leading to a collapse in a scenario sometimes called the Big Crunch. In such a model, the universe would have a symmetrical life cycle, beginning with expansion and ending with contraction. However, observations in the late 1990s changed this picture entirely. Scientists discovered that not only is the universe expanding, but the rate of expansion is accelerating. This acceleration is driven by a mysterious and invisible force known as dark energy. Unlike matter and radiation, dark energy does not clump together or form structures. Instead, it appears to be a property of space itself, uniformly filling the universe and pushing it apart on the largest scales. The more space there is, the more dark energy there seems to be, and the stronger its effect becomes. This creates a runaway expansion, where the universe stretches faster and faster as time progresses. It is as if the very fabric of reality is under a constant, invisible tension that pulls everything apart. The implications of this discovery are enormous. If the expansion continues to accelerate indefinitely, the universe will gradually become more isolated and empty. Distant galaxies will move away from us faster than their light can reach us, meaning that over time, they will disappear from our observable horizon. This does not mean they vanish physically, but rather that their light will never reach us again. The observable universe will shrink from our perspective, even as the total universe continues to expand. Eventually, only galaxies that are gravitationally bound to us, such as those in our local group, will remain visible. On the largest scales, galaxy clusters are the building blocks of the cosmic web. These clusters are gravitationally bound collections of galaxies, sometimes containing thousands of individual systems. At present, many of these clusters are still connected through weak gravitational interactions, forming a vast network across space. However, as expansion accelerates, even these structures will begin to drift apart. The gravitational bonds that hold them together will eventually be overcome by the stretching of space itself. Over billions of years, clusters will become isolated islands in an ever-expanding ocean of emptiness. From the perspective of an observer within a galaxy cluster, the night sky will slowly change. Distant galaxies will become dimmer and redshifted, their light stretched into longer wavelengths as space expands during its journey. This redshift is one of the key pieces of evidence for cosmic expansion. It tells us that galaxies are moving away from us, and the farther they are, the faster they recede. In the distant future, this effect will become so extreme that even visible light from faraway galaxies will be stretched into infrared, then microwave, and eventually radio wavelengths, until it becomes undetectable with any practical technology. As time continues, the universe will enter what can be described as a phase of cosmic isolation. Each gravitationally bound system will become increasingly cut off from all others. For example, our own Milky Way galaxy is part of a local group that includes Andromeda and several smaller galaxies. Over billions of years, the Milky Way and Andromeda will collide and merge into a single large elliptical galaxy. After this event, the merged system will remain bound, but everything outside it will continue to drift away, disappearing beyond the cosmic horizon. Future observers within this merged galaxy will see an increasingly empty universe, with fewer and fewer external galaxies visible. The expansion of the universe does not affect local structures in the same way. At small scales, gravity is strong enough to hold systems together. Planets remain bound to stars. Stars remain bound to galaxies, and galaxies remain bound in clusters. The expansion becomes significant only on the largest scales, where the distances are so vast that even gravity cannot overcome the stretching of space. This means that while the universe as a whole is expanding, local regions remain stable. However, this stability is temporary on cosmic timescales. As dark energy continues to dominate, the universe's large-scale structure will become increasingly simplified. The intricate web of filaments and clusters that currently defines cosmic architecture will gradually dissolve. These filaments are composed of galaxies and dark matter, forming vast interconnected networks across billions of light years. But in the far future, these connections will weaken and disappear. Each cluster will stand alone, surrounded by emptiness, like isolated cities in a desert that grows larger with every passing moment. One of the most profound consequences of this expansion is the change in the observable universe. At present, we can observe light that has traveled for billions of years, giving us a glimpse into the early universe. However, as expansion accelerates, there will come a point when light from distant regions will never reach us, no matter how long we wait. This creates a cosmic event horizon, beyond which information is permanently inaccessible. The universe beyond this horizon still exists, but it becomes forever hidden from view. In a sense, each region of space becomes trapped within its own observable bubble. If we imagine intelligent observers in the far future, their understanding of the universe would be drastically limited compared to ours. They might believe they live in a universe containing only their local galaxy cluster, with no evidence of a larger cosmic structure beyond it. The cosmic microwave background radiation, which today provides strong evidence for the Big Bang, would become so diluted and redshifted that it might become undetectable. This means that future civilizations could lose access to fundamental clues about the origin of the universe itself. The acceleration of expansion also affects time in a subtle way. While time itself continues at a constant rate locally, the changing structure of the universe alters the context in which events occur. As matter becomes more isolated and interactions become rarer, the universe transitions from a dynamic environment filled with change to one dominated by stillness. Processes that rely on energy differences become increasingly difficult to sustain. Stars burn out, black holes dominate, and eventually even these structures fade, leaving behind a cold and empty expanse. Dark energy remains, one of the greatest mysteries in physics. We do not know whether it is a constant property of space, a dynamic field that evolves over time, or something entirely different from our current understanding. Some theories suggest that dark energy might weaken in the far future, potentially slowing or even reversing expansion. Others propose that it could strengthen, leading to even more dramatic outcomes, such as a scenario called the Big Rip, where expansion becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atomic structures. However, current observations suggest a more stable form of dark energy consistent with a constant energy density filling space. If dark energy remains constant, the universe will continue its path toward increasing isolation and emptiness. Over trillions of years, galaxies outside local clusters will vanish from view. Star formation will cease as gas reservoirs are exhausted. Existing stars will burn out one by one. Eventually, only remnants such as white dwarfs, neutron stars, and black holes will remain. Even these objects will slowly decay or merge, leading to an increasingly simple cosmic landscape. The expansion of the universe is not just a physical process, but also a philosophical one. It forces us to confront the idea that everything we see is temporary on cosmic timescales. The structures that seem permanent, galaxies, stars, and even black holes, are part of a larger evolutionary process that leads toward transformation and eventual decay. Yet within this vast and expanding framework, complexity still arises, at least for a time. Stars shine, planets form, and life emerges in rare and extraordinary circumstances. Our current moment in cosmic history is unique because we exist during the era of peak structure formation. Galaxies are still active, stars are still being born, and the universe is still rich with energy gradients that allow complexity to exist. In the distant future, this will no longer be the case. The universe will become progressively more uniform, more diluted, and more inert. Expansion is the mechanism that drives this transformation, slowly but relentlessly shaping the destiny of everything that exists. As we move deeper into this journey through time, the focus will shift from large-scale expansion to the life cycles of stars, the engines that light up the universe and drive its evolution. Understanding how stars are born, live, and die will reveal the next layer of cosmic transformation, one that plays a crucial role in shaping the future universe we are trying to imagine. The expansion continues, silent and unstoppable, stretching the fabric of reality into an ever-growing emptiness. In the vast unfolding story of the universe, stars are among the most important actors. They are the engines of light, the forgers of elements, and the architects of cosmic structure. Without stars, the universe would be dark, cold, and chemically simple. With them, it becomes dynamic, colorful, and capable of producing planets, complex chemistry, and eventually, life. Yet stars are not eternal. They are born, they live, and they die according to the laws of physics that govern energy, pressure, and gravity. Understanding the fate of stars is essential to understanding the future of the universe itself, because as stars fade away, the entire cosmic landscape begins to change in fundamental ways. Stars are born in enormous clouds of gas and dust, known as nebulae. These regions exist throughout galaxies, especially in spiral arms where material is more densely concentrated. Over time, gravity begins to pull this gas together. Small fluctuations in density grow stronger as more material is attracted to the same region. Eventually, a collapsing clump of gas forms a protostar, a hot and dense object that continues to gather mass from its surroundings. As pressure and temperature rise in its core, nuclear fusion ignites. This marks the birth of a star. Nuclear fusion is the process that powers all stars. In the core of a star, hydrogen atoms are fused together to form helium, releasing enormous amounts of energy in the process. This energy flows outward and creates a balance between gravity, which pulls matter inward, and radiation pressure, which pushes outward. This delicate balance keeps the star stable for most of its life. As long as hydrogen fuel remains in the core, the star continues to shine. This phase of a star's life is known as the main sequence, and it represents the longest and most stable period in its existence. The lifetime of a star depends primarily on its mass. Massive stars burn their fuel quickly because their cores are under extreme pressure and temperature. As a result, they shine brightly but live relatively short lives, sometimes only a few million years. Smaller stars, on the other hand, burn their fuel slowly and can live for tens of billions or even trillions of years. These low-mass stars, often called red dwarfs, are the most common type of star in the universe and will outlive all other stellar populations by an enormous margin. As a star ages, it gradually changes. The hydrogen in its core begins to run out, and fusion slows down. When this happens, gravity starts to compress the core again, causing it to heat up. In response, the outer layers of the star expand, and the star becomes a red giant. This phase is marked by dramatic changes in size and brightness. The star can grow to many times its original diameter, sometimes engulfing nearby planets in the process. Our own Sun will eventually enter this phase in about 5 billion years, expanding far beyond its current size. During the red giant phase, the star begins fusing helium into heavier elements such as carbon and oxygen. However, this process cannot continue indefinitely for smaller stars. Once the fuel is exhausted, the star sheds its outer layers into space, creating a beautiful expanding shell of gas known as a planetary nebula. What remains is the core of the star, a dense and hot object called a white dwarf. A white dwarf no longer produces energy through fusion. Instead, it slowly cools and fades over time, radiating away its remaining heat into the coldness of space. For more massive stars, the end is far more violent. When their cores can no longer support fusion reactions, they collapse under gravity in a fraction of a second. This collapse triggers a massive explosion known as a supernova. A supernova releases more energy in a few moments than the Sun will produce in its entire lifetime. The explosion blasts the outer layers of the star into space, enriching the surrounding environment with heavy elements such as iron, gold, and uranium. These elements become the building blocks for future stars, planets, and even life. The core left behind after a supernova can become one of two extreme objects, depending on its mass. If the core is not too massive, it becomes a neutron star, an incredibly dense object composed almost entirely of neutrons packed tightly together. A neutron star can have more mass than the Sun, but be only about the size of a city. Its density is so extreme that a teaspoon of its material would weigh billions of tons on Earth. If the core is even more massive, it collapses further into a black hole, a region of space where gravity becomes so strong that nothing can escape it. These stellar remnants are not just endpoints, they are also important participants in the long-term evolution of the universe. White dwarfs slowly cool over trillions of years, eventually becoming cold black dwarfs, though the universe is not yet old enough for any black dwarfs to exist. Neutron stars can collide with each other, producing bursts of energy and creating heavy elements. Black holes can merge and grow, influencing the structure of galaxies. Even after stars die, their remnants continue to shape the cosmic environment. In the current universe, star formation is still actively occurring. Vast clouds of gas continue to collapse and form new stars in many galaxies. However, this process is already slowing down compared to the past. The universe reached its peak star formation rate billions of years ago, and since then the rate has been declining. This decline is significant because it marks the beginning of the end of the stellar era. As the universe expands and gas becomes more dispersed, it becomes harder for gravity to gather enough material to form new stars. Eventually, star formation will come to an end entirely. The gas needed to create new stars will either be locked up in planets, ejected into intergalactic space, or consumed by existing stars and black holes. Without new stars being born, the stellar population of the universe will slowly age. Massive stars will die first, followed by medium-sized stars. Only the smallest and longest-lived red dwarfs will remain, continuing to shine faintly for trillions of years. As time progresses further, even these red dwarfs will exhaust their fuel. They will transition into white dwarfs, leaving behind a universe filled with stellar remnants rather than active stars. This marks a fundamental shift in the nature of the cosmos. The universe will no longer be powered by nuclear fusion on a large scale. Instead, it will be dominated by slowly cooling objects that no longer produce new energy. Light will become increasingly rare, and darkness will begin to dominate the cosmic landscape. The death of stars also has profound implications for galaxies. Stars are the primary sources of light and energy in galaxies, and they help define the structure and appearance of these massive systems. As stars die, galaxies will gradually fade. Spiral arms will lose their brightness, star clusters will dissolve, and the overall glow of galaxies will diminish. In the far future, galaxies will no longer appear as bright, structured systems, but rather as collections of faint remnants surrounding central black holes. One of the most important roles of stars is the creation of heavy elements. Without stars, the universe would consist mostly of hydrogen and helium, the simplest elements formed in the early universe. It is inside stars that heavier elements are forged through nuclear fusion and supernova explosions. These elements are essential for the formation of planets, rocky surfaces, and complex chemistry. Every atom of carbon in living organisms, every atom of oxygen in water, and every atom of iron in blood was created inside a star. As stars die and no new ones are born, the production of these elements will cease, marking the end of chemical evolution on cosmic scales. In the distant future, the universe will contain all the elements needed for complexity, but they will no longer be actively recycled through stellar processes. Instead, they will exist in a static and decaying environment. Planets may still exist around long-lived stars or stellar remnants, but without new energy input from fusion, these systems will gradually become cold and inactive. The conditions that allow life, at least as we understand it, will become increasingly rare. The life cycle of stars is not just a sequence of physical events, it is also a story of transformation and impermanence. Stars begin as diffuse clouds of gas and end as compact remnants of extreme density or complete collapse. Along the way, they shape galaxies, create elements, and provide energy for countless processes. Yet, their existence is temporary on cosmic timescales. Even the longest-lived stars will eventually fade, contributing to the slow transition of the universe toward darkness and stillness. As we continue this journey through the future of the universe, we will next explore the most extreme objects left behind by dying stars, black holes. These mysterious regions of space represent the final stage of gravitational collapse and play a crucial role in the far future evolution of everything that exists. In the aftermath of stellar death, when stars have exhausted their nuclear fuel and either collapsed or shed their outer layers, the universe does not fall silent immediately. Instead, it enters a phase dominated by the most extreme objects known to physics, black holes. These entities are not merely remnants of massive stars, but fundamental distortions in space-time itself, where gravity has become so intense that the usual rules of physics break down at the boundary of what we can observe. To understand the future of the universe, one must understand black holes not as isolated curiosities, but as long-term cosmic engines that will gradually reshape everything that remains. A black hole forms when a sufficiently massive star reaches the end of its life and undergoes gravitational collapse. When nuclear fusion can no longer generate enough outward pressure to counteract gravity, the core of the star collapses inward. If the remaining mass is above a certain threshold, no known force can stop this collapse. The matter is compressed into an extremely small region, creating a point of infinite density known as a singularity, surrounded by an invisible boundary called the event horizon. The event horizon marks the point of no return. Anything that crosses it, including light, cannot escape. What makes black holes so fascinating is not only their destructive power, but also their simplicity. Once formed, a black hole can be described by just a few properties: mass, spin, and electric charge. Everything else about the matter that created it becomes hidden behind the event horizon. In a sense, black holes erase the detailed history of the objects that formed them, preserving only the most basic information. This property makes them both mysterious and fundamental in understanding the nature of space, time, and information. In the current universe, black holes exist in many sizes. Stellar mass black holes form from the collapse of massive stars, typically containing a few times the mass of the Sun. These are scattered throughout galaxies, often in binary systems or surrounded by remnants of their progenitor stars. At the centers of most galaxies, however, lie supermassive black holes. These giants contain millions or even billions of times the mass of the Sun. Their origin is still not fully understood, but they likely grew over billions of years by consuming gas, stars, and even other black holes. These supermassive black holes play a central role in the structure of galaxies. They influence the motion of stars in galactic cores and can regulate star formation by controlling the flow of gas. In some cases, they power quasars, extremely bright objects formed when matter falling into a black hole heats up and emits enormous amounts of radiation before crossing the event horizon. Quasars were much more common in the early universe when galaxies were younger and more active. Today, most supermassive black holes are relatively quiet, but they remain powerful gravitational anchors. As the universe evolves, black holes will become increasingly important. While stars fade and new star formation declines, black holes will persist. Unlike stars, which require fuel to shine, black holes are not dependent on fusion or external energy sources. They simply exist as regions of warped space-time. Over time, they will begin to dominate the mass content of the universe. Stars, planets, and gas clouds will either be consumed by them or drift away due to cosmic expansion. One of the most important processes involving black holes is accretion. When matter falls toward a black hole, it does not immediately disappear. Instead, it forms a rotating disk known as an accretion disk. Friction and gravitational forces within this disk heat the material to extremely high temperatures, causing it to emit intense radiation, often in the form of X-rays. This process can make black holes some of the brightest objects in the universe, even though the black hole itself emits no light. However, accretion requires available matter. As the universe ages and matter becomes more dispersed, accretion will become less common. Eventually, most black holes will be left in relative isolation, surrounded by empty space. But even in this quiet state, they are not truly permanent. According to quantum theory, black holes are not completely black. Instead, they slowly emit radiation through a process known as Hawking radiation. This phenomenon arises from quantum effects near the event horizon, where particle pairs can form and one particle falls into the black hole while the other escapes. Over extremely long timescales, this leads to a gradual loss of mass. Hawking radiation is incredibly weak for large black holes, making it impossible to observe directly in current astronomical systems. However, over trillions upon trillions of years, it becomes the dominant process governing black hole evolution. As black holes lose mass, they shrink and their radiation increases. This creates a slow but accelerating evaporation process. Eventually, even the largest black holes will completely disappear, releasing their remaining energy back into space. The timescale for black hole evaporation is vastly longer than the current age of the universe. Stellar mass black holes may take around 10 to the power of 67 years to evaporate, while supermassive black holes could take up to 10 to the power of 100 years or more. These numbers are so large that they are difficult to comprehend in any human sense. Yet, in the far future timeline of the universe, they represent a crucial transition from a black hole-dominated cosmos to one that is nearly empty. Before this final evaporation occurs, black holes will interact in various ways. They can merge when they come close enough to each other, releasing enormous amounts of energy in the form of gravitational waves. These waves are ripples in space-time itself, traveling at the speed of light. In the present universe, we have already detected such events using instruments like LIGO and Virgo, confirming that black holes can collide and combine. In the distant future, as stars and other objects disappear, black hole mergers may become one of the last major energetic events in the universe. As time continues, most matter will either fall into black holes or drift far away due to cosmic expansion. Galaxies will lose their structure as stars die and orbits become disrupted. Eventually, each galaxy will be dominated by a central supermassive black hole surrounded by scattered remnants. Over even longer timescales, these black holes may capture the remaining matter in their vicinity, growing slowly before beginning their long evaporation process. One of the most profound aspects of black holes is their relationship with information. When matter falls into a black hole, it seems that the information describing that matter is lost. This creates what is known as the black hole information paradox. According to quantum mechanics, information cannot be destroyed, yet black holes appear to erase it. Hawking radiation suggests that information might be preserved in subtle correlations within the emitted radiation, but this remains an area of active research in theoretical physics. The resolution of this paradox is expected to reveal deep insights into the nature of reality. In the far future universe, black holes will represent the final stage of organized structure. Once stars are gone and galaxies have faded, black holes will be the last remaining significant gravitational objects. They will drift slowly through an expanding and increasingly empty space, occasionally merging or capturing stray particles, but even this stage is temporary. As Hawking radiation continues its slow process, black holes will gradually shrink and disappear. When the last black hole evaporates, the universe will undergo a dramatic transformation. All that will remain is a thin background of radiation, low-energy particles, and an expanding fabric of space that contains almost no structure. This marks the transition from a universe shaped by gravity and matter to one dominated by entropy and near-complete emptiness. The disappearance of black holes represents the end of the most massive and influential objects in cosmic history. It is important to understand that black holes are not just destructive endpoints, they are also part of the recycling process of the universe. Through accretion, mergers, and radiation, they redistribute energy and matter over vast timescales. They also serve as laboratories for extreme physics, where gravity, quantum mechanics, and thermodynamics intersect. Many of the deepest questions in physics are tied to understanding what happens inside and around black holes. As we move further into the future of the universe, black holes mark a critical bridge between the era of stars and the final eras of cosmic evolution. They represent both the remnants of past stellar activity and the last active players in a fading universe. Their eventual evaporation signals the beginning of a new phase, one where even gravity loses its dominant role in shaping structure. In the next stage of this journey, we will explore what happens after black holes fade away, when the universe enters a state dominated by dark energy and extreme isolation. This will lead us toward a cosmos that is increasingly empty, cold, and silent, moving closer to the ultimate fate of all physical processes. As the universe continues its relentless expansion and the last generations of stars fade into darkness, a profound transformation begins to take shape on the largest scales. Galaxies, once vibrant cities of billions of stars, begin to drift away from one another. The cosmic web that once connected them through vast filaments of gas and dark matter starts to unravel. What remains is a universe that no longer resembles the structured and luminous cosmos we observe today, but instead becomes increasingly fragmented and isolated. This stage is known as the galaxy isolation era, and it represents one of the most significant turning points in the long-term evolution of everything that exists. To understand galaxy isolation, we must first appreciate how galaxies are organized in the present universe. Galaxies are not randomly scattered in space. They are grouped into clusters, which themselves form larger structures called superclusters. These superclusters are connected by filaments of dark matter and gas, forming a vast cosmic web that spans billions of light years. Within this web, galaxies interact, collide, merge, and exchange material. Gravity plays a central role in maintaining these connections, pulling structures together even as the universe expands. However, the expansion of the universe is not uniform in its effects. On small scales, gravity dominates. This is why galaxies, solar systems, and planetary systems remain stable. But on extremely large scales, the expansion of space itself becomes the dominant force. As dark energy continues to accelerate this expansion, it begins to overcome even the weak gravitational ties that connect galaxy clusters. Over time, these structures are stretched farther and farther apart until the bonds between them are effectively broken. At first, this process is extremely slow and nearly unnoticeable. Galaxies within a cluster remain bound together, continuing their complex dances of orbit and interaction. But the spaces between clusters begin to grow at an accelerating rate. Light traveling between distant clusters becomes increasingly redshifted and faint. Eventually, it becomes impossible for signals to travel from one cluster to another. Each cluster becomes an isolated island of matter, cut off from the rest of the universe by expanding space. From the perspective of an observer within a galaxy cluster, the night sky begins to change in subtle but profound ways. Distant galaxies outside the cluster slowly fade away. Their light becomes stretched into longer wavelengths, moving beyond the visible spectrum into infrared and radio frequencies. At first, advanced telescopes might still detect them, but over time, even these instruments will fail to pick up any meaningful signal. The universe beyond the local cluster effectively disappears from view, not because it ceases to exist, but because its light can no longer reach the observer. This loss of visibility has deep implications for the understanding of the universe itself. Future observers living in such isolated clusters may have no evidence that other galaxies exist at all. Their observable universe would consist only of their own gravitationally bound system. Without external references, the large-scale structure of the cosmos would be invisible. The idea of a vast, expanding universe filled with billions of galaxies might become unknown or even unimaginable. Within each isolated galaxy cluster, internal evolution continues for some time. Galaxies still interact with one another, especially within dense clusters. Collisions and mergers remain common events. For example, in our own local group, the Milky Way and Andromeda galaxies are expected to collide in several billion years, eventually merging into a single large elliptical galaxy. This merged system, sometimes referred to as Milkomeda, will become the dominant structure in our local region of the universe. After this event, no other external galaxies will be visible from within it. As galaxy clusters become isolated, their internal dynamics begin to simplify. Without external gravitational influences, clusters settle into stable configurations, dominated by a few large galaxies and a central supermassive black hole. Smaller galaxies are gradually absorbed or disrupted. Over long timescales, the structure of these clusters becomes smoother and more relaxed, as interactions slowly diminish. One of the key features of this era is the gradual disappearance of intergalactic gas. In the present universe, galaxy clusters still contain hot gas that emits X-rays and contributes to ongoing star formation. However, as time progresses, this gas is either consumed by stars, ejected into space, or drawn into black holes. Without a fresh supply of material from outside the cluster, the remaining gas becomes increasingly scarce. This leads to a decline in star formation, eventually bringing it to a complete halt. Once star formation ends, the existing stars within galaxies continue their natural life cycles. Massive stars die quickly, leaving behind neutron stars or black holes. Medium-sized stars, like the Sun, evolve into white dwarfs. Only the smallest red dwarf stars remain active for extremely long periods, slowly burning their hydrogen fuel over trillions of years. However, even these long-lived stars are not permanent. Eventually, they too will exhaust their fuel and fade into darkness. As the stellar population ages, galaxies begin to lose their brightness. The spiral arms that once glowed with young stars and nebulae become faint and diffuse. Star clusters dissolve over time, and the overall structure of galaxies becomes less distinct. What remains are large collections of stellar remnants, including white dwarfs, neutron stars, and black holes, all orbiting in a slowly evolving gravitational system. Dark energy continues to play a crucial role in this transformation. Even though galaxy clusters remain gravitationally bound, the space between clusters expands at an accelerating rate. This means that while internal structures remain stable for long periods, their isolation from the rest of the universe becomes absolute. No new matter enters the clusters from outside, and no information escapes beyond their cosmic horizon. Each cluster becomes a self-contained universe in its own right. In this isolated state, the concept of a cosmic horizon becomes increasingly important. The cosmic horizon defines the limit beyond which events cannot influence an observer due to the expansion of space. In the galaxy isolation era, this horizon shrinks relative to the scale of the universe, enclosing each cluster within its own observable boundary. Everything beyond this boundary is not only unreachable, but also permanently unobservable. The implications of this are profound. Imagine a future civilization that evolves within an isolated galaxy cluster. Their entire understanding of reality would be based on the limited region they can observe. Without knowledge of other clusters, they might assume that their local group is the entirety of existence. The evidence of a larger universe, such as the cosmic microwave background radiation or the distribution of distant galaxies, would be lost to them due to extreme redshift and dilution. Their cosmology would be fundamentally incomplete, shaped by the constraints of their isolated environment. As time continues, even within these isolated clusters, entropy increases. Black holes slowly grow by absorbing nearby matter. Stars continue to die, leaving behind remnants that no longer produce energy through fusion. Planetary systems may still exist for a time, but without stellar energy input, they become cold and inactive. Over extremely long timescales, even gravitational interactions within clusters begin to weaken as objects are ejected or absorbed by central black holes. Eventually, most matter within a galaxy cluster will be either part of a black hole or drifting as isolated remnants. The cluster itself becomes dominated by a few massive black holes surrounded by sparse distributions of stellar debris. These black holes will continue to interact, sometimes merging and releasing gravitational waves, but such events become increasingly rare as time progresses. The galaxy isolation era is not a sudden transition, but a gradual fading of cosmic connectivity. It represents the breakdown of the large-scale structure of the universe into independent units. Each cluster becomes a separate island of matter in an expanding sea of space. Communication between these islands becomes impossible, and eventually even observation of them becomes impossible, as light is stretched beyond detectability. What makes this era particularly striking is the change in perspective it creates. In the current universe, we can observe billions of galaxies and reconstruct the history of cosmic evolution. But in the galaxy isolation era, future observers will lose access to this broader context. Their universe will appear finite, static, and self-contained. The rich structure we see today will be gone, replaced by a simplified and isolated cosmic environment. As we move further along the timeline of the universe, this isolation sets the stage for the next major transformation. The remaining galaxies will continue to evolve internally, but their connection to the wider cosmos will be permanently severed. This leads into the next phase, where the universe is dominated by aging stars, fading light, and the growing influence of dark energy on increasingly empty space. The galaxy isolation era marks the beginning of the end of cosmic structure on the largest scales. It is the moment when the universe stops being a connected web of galaxies and becomes instead a collection of separated islands, drifting ever farther apart, each slowly moving toward its own quiet and inevitable fate. After the grand separation of galaxies and the collapse of cosmic connectivity, the universe enters a far more subdued and prolonged phase. This is the degenerate era, a time when the brilliance of stars has largely faded and the universe is dominated not by glowing nuclear furnaces, but by their remnants. It is an era defined by endurance rather than creation, by slow cooling rather than energetic transformation, and by the gradual dominance of the most stable and long-lived forms of matter left behind after stellar evolution. To understand the degenerate era, it is important to recognize what degenerate matter means in astrophysics. This is not a term about decay in the everyday sense, but rather a description of a quantum state of matter under extreme pressure. In ordinary stars, thermal pressure from nuclear fusion keeps matter in a gaseous plasma state. But when stars die and fusion ceases, gravity can compress matter into much denser forms. In these conditions, the rules of quantum mechanics take over, especially the Pauli exclusion principle, which prevents identical particles such as electrons or neutrons from occupying the same quantum state. This creates a new kind of pressure known as degeneracy pressure, which supports objects like white dwarfs and neutron stars against further collapse. White dwarfs are among the most common stellar remnants in the universe. They form when stars similar in mass to the Sun exhaust their nuclear fuel. After shedding their outer layers as a planetary nebula, the remaining core collapses into a dense, Earth-sized object composed mostly of carbon and oxygen nuclei embedded in a sea of degenerate electrons. Although no fusion occurs inside a white dwarf, it remains extremely hot at formation and slowly cools over time, radiating away its stored thermal energy into space. In the early stages of the degenerate era, white dwarfs still glow faintly. They are dim but detectable, remnants of once vibrant stars. However, as time progresses, they cool steadily. Without any internal energy source, they gradually lose heat until they become cold, dark objects known as black dwarfs. A black dwarf is a theoretical final stage of a white dwarf, representing a stellar remnant that has reached thermal equilibrium with the surrounding universe. The universe is not yet old enough for any black dwarfs to exist, but in the degenerate era they will begin to dominate the stellar population. Neutron stars represent another extreme form of degenerate matter. These objects form when massive stars undergo supernova explosions and their cores collapse under gravity beyond the white dwarf stage. In neutron stars, electrons and protons are crushed together to form neutrons, resulting in an object composed almost entirely of tightly packed nuclear matter. The density of a neutron star is so extreme that a teaspoon of its material would weigh billions of tons on Earth. Despite their small size, typically only about 20 kilometers in diameter, neutron stars can contain more mass than the Sunday. Neutron stars also possess incredibly strong magnetic fields and can rotate at extremely high speeds. Some emit beams of radiation that sweep across space like cosmic lighthouses, known as pulsars. In the present universe, pulsars are still observed and studied, providing valuable insights into extreme physics. However, in the degenerate era, even neutron stars will gradually lose energy. Their rotation will slow, their magnetic fields will weaken, and they will eventually become inert, cold remnants drifting through space. Black holes, which were discussed in the previous chapter, continue to play a central role in this era as well. Although they are not traditionally classified as degenerate matter in the same way as white dwarfs or neutron stars, they are the ultimate end state of gravitational collapse. In the degenerate era, black holes will be among the most massive and influential objects remaining. They will continue to grow by absorbing surrounding matter, including stray stars, planets, and compact remnants that wander too close to their gravitational influence. However, the environment of the degenerate era is already extremely sparse. Star formation has long ceased. The gas that once filled galaxies has been either consumed or expelled. Most of the luminous structures that defined earlier cosmic eras have disappeared. What remains is a universe populated primarily by isolated stellar remnants, slowly interacting under the influence of gravity. One of the defining characteristics of the degenerate era is the extreme time scale on which processes occur. Unlike earlier epochs where stellar evolution happened over millions or billions of years, the degenerate era stretches across timescales of trillions to quadrillions of years. Physical processes become increasingly rare and slow. Collisions between objects are infrequent. Even the motion of stars and remnants becomes more predictable and stable as gravitational systems settle into long-term equilibrium. Within galaxies, now already isolated from the wider universe due to cosmic expansion, the structure becomes dominated by a few key components. At the center lies a supermassive black hole, the remnant of billions of years of galactic evolution. Surrounding it are sparse distributions of white dwarfs, neutron stars, and occasional rogue planets or stellar remnants. These objects orbit in a slowly evolving gravitational environment, occasionally interacting through close encounters or mergers, but most of the time simply drifting in vast empty space. White dwarfs, in particular, become the most common visible objects in this era. They represent the final stage of most stars that were not massive enough to form neutron stars or black holes. Over time, these white dwarfs continue to cool and fade. Their luminosity decreases steadily, and their temperature drops toward the background temperature of the universe. Eventually, they will become invisible to any form of electromagnetic observation, effectively turning into cold, dark spheres of degenerate matter. Neutron stars follow a similar trajectory, though their initial conditions are more extreme. Their strong magnetic fields and rapid rotation gradually decay over time. As they lose energy, they become less active and eventually indistinguishable from other dark remnants. In the absence of external energy sources, even their exotic properties fade into a quiet, inert state. Despite the overall decline in activity, occasional dramatic events still occur in the degenerate era. For example, binary systems composed of two white dwarfs or two neutron stars may gradually lose energy through gravitational wave emission, causing them to spiral inward and eventually merge. Such mergers can produce powerful bursts of energy, sometimes reigniting nuclear reactions temporarily or forming new compact objects. These events, however, become increasingly rare as the population of interacting objects diminishes. Black holes remain the ultimate repositories of mass in the degenerate era. Over time, they absorb much of the remaining matter in their local environments. Smaller black holes may merge with larger ones, forming even more massive structures. This process leads to the growth of increasingly dominant central black holes within galaxies. However, even this growth is limited by the scarcity of available matter. One of the most important transitions during this era is the increasing role of entropy. Entropy, in thermodynamic terms, is a measure of disorder, or the number of possible microscopic configurations of a system. As the universe evolves, entropy increases. In the degenerate era, entropy is already extremely high compared to earlier periods. Most energy gradients have been exhausted, and systems tend toward equilibrium. This means that there are fewer opportunities for work to be performed, fewer sources of usable energy, and fewer dynamic processes capable of sustaining complexity. The universe in this era is not chaotic in the sense of being turbulent. Instead, it is uniformly quiet, with rare pockets of activity separated by vast regions of emptiness. The remaining structures are stable but inactive. A white dwarf does not explode or change significantly over long periods. A neutron star does not evolve rapidly. A black hole does not emit light or energy in any traditional sense. The universe becomes a landscape of frozen remnants slowly drifting through expanding space. Cosmic expansion continues to play a background role in this era. Even though galaxies are already isolated, the space within and between structures continues to expand due to dark energy. This expansion further reduces the likelihood of interactions between objects. Over extremely long timescales, even gravitationally bound systems may be affected as distances increase and weakly bound objects are lost to the expanding fabric of space. One of the most profound aspects of the degenerate era is the loss of time-dependent structure. In earlier eras, time was marked by change. Stars formed and died, galaxies collided, and energetic processes reshaped the universe. In the degenerate era, change becomes increasingly rare. Time continues to pass, but the universe changes very little in observable ways. This creates a sense of temporal flattening, where the distinction between moments becomes less meaningful in terms of physical processes. Life, as far as current scientific understanding suggests, becomes increasingly unlikely in this era. The conditions required for stable energy sources, chemical complexity, and long-term environmental stability are largely absent. Any hypothetical civilizations that might exist in this era would face extreme challenges in accessing energy and maintaining complex structures. Most regions of the universe would be too cold, too isolated, and too devoid of usable energy gradients to support long-term activity. As the degenerate era progresses, it sets the stage for the next and even more extreme phase of cosmic evolution, the black hole era. In this upcoming stage, black holes will dominate the universe almost completely, consuming the remaining matter and becoming the primary structures shaping space-time. The transition from degenerate matter to black hole dominance marks one of the final steps in the long journey from a vibrant, star-filled cosmos to a universe approaching ultimate emptiness. The degenerate era is, in essence, the quiet aftermath of cosmic activity. It is the long twilight period following the death of stars and the isolation of galaxies, where the universe is filled with relics of its past rather than active processes of creation. It is a universe that remembers its history only through the remnants left behind, slowly cooling, slowly drifting, and slowly fading into deeper stages of cosmic time. As the universe continues its long descent into silence, even the remnants of stars begin to lose their dominance. White dwarfs cool, neutron stars fade into quiet isolation, and galaxies become little more than sparse collections of dark objects drifting through expanding space. Yet even in this fading landscape, there remains one class of objects capable of shaping the future on the largest scales. These are black holes, and in the next phase of cosmic evolution, they become the central actors of reality itself. This is the black hole era, a time when gravity's most extreme manifestation defines almost everything that remains in the universe. To understand this era, it is important to realize that black holes do not age in the same way stars do. Stars live by burning fuel, gradually changing as they consume hydrogen and heavier elements. Black holes, by contrast, do not burn, shine, or undergo internal nuclear processes. Once formed, they are fundamentally stable objects governed primarily by their mass, spin, and charge. This stability allows them to persist long after all other astrophysical structures have faded. In a universe where stars no longer shine and galaxies no longer form new structures, black holes remain as the last significant reservoirs of mass and gravitational influence. In the black hole era, the universe is already extremely old. All star formation has long ceased. The remaining white dwarfs and neutron stars from the degenerate era have either cooled into inert states or been consumed by gravitational interactions. What remains are scattered stellar remnants, rogue planets, and massive black holes occupying the centers of what were once galaxies. These black holes, both stellar mass and supermassive, become the dominant structures shaping the evolution of matter. One of the key processes defining this era is accretion, the gradual accumulation of matter by black holes. Even though the universe is extremely empty at this stage, there are still occasional sources of material. Rogue objects, such as cold planets, asteroids, and dead stars, drift through space on random trajectories. When these objects come too close to a black hole, they are captured by its gravitational field. As they fall inward, they are stretched and torn apart in a process known as spaghettification, eventually forming a hot accretion disk before crossing the event horizon. These accretion disks are among the last sources of luminous energy in the universe. As matter spirals into a black hole, friction and gravitational forces heat it to extreme temperatures, causing it to emit radiation across the electromagnetic spectrum. In earlier cosmic eras, accretion disks around black holes could outshine entire galaxies. In the black hole era, however, such events become increasingly rare. The supply of matter feeding these disks steadily declines, and with it, the brightness of the universe fades further. Supermassive black holes, located at the centers of former galaxies, play a particularly important role in this era. These giants, containing millions or billions of solar masses, act as gravitational anchors for their local environments. Even as the surrounding galaxy dissolves into darkness, the central black hole remains, slowly growing as it consumes any remaining matter. Over immense timescales, these black holes may merge with one another if their host systems interact, creating even larger and more massive objects. The merger of black holes is one of the most dramatic events that still occurs in this late stage of cosmic evolution. When two black holes orbit each other closely enough, they lose energy through the emission of gravitational waves. These waves are ripples in space-time that carry energy away from the system, causing the black holes to spiral inward and eventually collide. The final merger releases a burst of gravitational radiation that can momentarily distort the structure of space-time itself across vast regions of the universe. In the present era of human observation, such events have already been detected by instruments like LIGO and Virgo, confirming the existence of gravitational waves. In the black hole era, however, these mergers become one of the few remaining energetic events in an otherwise quiet universe. As black holes become more isolated, mergers become less frequent, but when they do occur, they represent the final moments of large-scale dynamical activity. Over time, black holes dominate not only the mass of the universe, but also its structure. Most remaining matter is either captured by black holes or exists as isolated particles drifting through space. Galaxies no longer exist as coherent luminous structures. Instead, what once were galaxies are now vast regions, dominated by a central black hole surrounded by extremely sparse distributions of debris. These regions are separated by enormous distances due to cosmic expansion, making interactions between them increasingly rare. As black holes continue to absorb matter, they slowly grow in mass. However, this growth is limited by the scarcity of available material. Eventually, even the largest black holes exhaust their local environments. At this point, they enter a long period of relative isolation. They no longer accrete significant amounts of matter and instead exist as dormant gravitational objects drifting through an expanding universe. Despite their apparent permanence, black holes are not truly eternal. One of the most important discoveries in theoretical physics is that black holes emit a very faint form of radiation known as Hawking radiation. This process arises from quantum effects near the event horizon, where particle pairs can form and one particle escapes while the other falls into the black hole. Over extremely long timescales, this leads to a gradual loss of mass and energy from the black hole. Hawking radiation is extraordinarily weak for large black holes, making it negligible on any timescale relevant to earlier cosmic eras. However, in the black hole era, where time stretches into trillions upon trillions of years, it becomes the dominant process governing black hole evolution. As black holes lose mass, they slowly shrink, and their radiation increases in intensity. This creates a feedback loop in which evaporation accelerates over time. The time scale for black hole evaporation is immense. A stellar mass black hole may take around 10 to the power of 67 years to fully evaporate, while a supermassive black hole may take up to 10 to the power of 100 years or more. These numbers far exceed any familiar cosmic timescale, yet they represent the final stage of black hole existence. In the black hole era, evaporation is the ultimate fate of all such objects. As black holes evaporate, they release their remaining energy back into the universe in the form of low-energy particles and radiation. This process marks one of the last significant redistributions of energy in cosmic history. After evaporation, nothing remains of the black hole except the radiation it emitted during its final moments. Even this radiation becomes increasingly diluted as the universe continues to expand. The black hole era is therefore a time of gradual simplification. At the beginning of the era, the universe still contains a variety of structures, including massive black holes, stellar remnants, and scattered matter. By the end, only black holes remain. And eventually, even these disappear, leaving behind an almost empty universe dominated by low-energy particles and radiation. One of the most profound aspects of this era is the change in the role of time. In earlier epochs, time was marked by constant change. The birth and death of stars, the formation of galaxies, and the dynamic evolution of cosmic structures. In the black hole era, change becomes increasingly rare. Black holes evolve slowly, mergers occur infrequently, and most regions of space remain static for vast periods. Time continues to pass, but it becomes less associated with observable events. Another important feature of this era is the increasing dominance of entropy. The universe is already in a high entropy state by the beginning of the black hole era, but it continues to move toward maximum entropy as black holes evaporate and matter becomes more evenly distributed. Once black holes disappear entirely, the universe approaches a state of near thermodynamic equilibrium, where no significant energy gradients remain to drive physical processes. It is also important to consider the role of cosmic expansion during this era. Dark energy continues to drive the accelerated expansion of space, causing distant regions of the universe to recede from one another at ever-increasing rates. This expansion ensures that even if some matter remains outside black holes, it becomes increasingly isolated and diluted over time. Eventually, the observable universe shrinks to a tiny region containing only a few gravitationally bound remnants before even those structures disappear. In this sense, the black hole era is both the peak and the beginning of the end of gravitational structure in the universe. Black holes represent the final stage of matter organized by gravity, and their eventual evaporation marks the transition to a universe where gravity no longer plays a significant role in shaping large-scale structure. As the last black holes evaporate, the universe enters its final transformation. What follows is no longer dominated by massive objects or gravitational interactions, but by a thin and expanding sea of radiation and particles. This sets the stage for the next era, where even black holes have vanished and the universe becomes a vast, cold, and nearly empty expanse. The black hole era is therefore not just a chapter in cosmic history, but a turning point. It represents the final stage in which the universe is still actively shaped by gravity and mass. Beyond it lies a cosmos that is increasingly featureless, where even the most extreme objects known to physics have completed their life cycle and disappeared into the fabric of expanding space. After the long dominance of black holes and their final evaporation, the universe enters a profoundly different phase. What remains is no longer shaped by stars, galaxies, or even gravity in any meaningful, large-scale way. Instead, the cosmos becomes a vast and expanding sea of extremely low-energy particles, photons stretched to enormous wavelengths, and a faint background of radiation diluted across an ever-growing space. This is the era where dark energy becomes the most important influence in the universe's behavior, not because it creates structures, but because it determines how space itself continues to evolve. This stage can be understood as the dark energy expansion era, a time when the universe is defined more by emptiness and separation than by any form of structure or activity. To understand this era, it is essential to revisit what dark energy represents. In modern cosmology, dark energy is the name given to the unknown force or property responsible for the accelerated expansion of the universe. Unlike matter, which clumps together under gravity, or radiation, which spreads and loses energy as it expands, dark energy appears to be uniform and constant throughout space. It does not dilute as the universe expands. Instead, its influence remains steady or even grows in effect relative to other forms of energy. This leads to a continuous acceleration of cosmic expansion, meaning that the farther apart objects are, the faster they move away from each other. In earlier eras, dark energy played a subtle but increasingly important role. During the galaxy isolation era, it was responsible for separating galaxy clusters. In the degenerate era, it ensured that structures remained isolated. In the black hole era, it contributed to the extreme separation of gravitational systems. Now, after the disappearance of black holes, dark energy becomes the dominant force shaping the entire universe on the largest scales. It determines not just the motion of galaxies or clusters, but the very structure of space-time itself. At this stage, the universe contains almost no bound structures. The last remnants of matter from evaporated black holes have been dispersed into extremely low-energy radiation and elementary particles. These particles are spread so thinly that interactions between them become extremely rare. Space is no longer filled with visible objects or energetic processes. Instead, it is a nearly uniform background of fading energy, expanding continuously in all directions. One of the most important consequences of dark energy-driven expansion is the creation of a cosmological event horizon. This horizon defines a boundary beyond which events cannot influence an observer, no matter how much time passes. In earlier eras, this horizon was already present but continually expanding as light from distant galaxies reached us. In the dark energy expansion era, however, the horizon becomes more fixed relative to local regions. As space expands faster than light can traverse it, more and more regions of the universe permanently disappear beyond observational reach. For any observer that might exist in this era, the observable universe becomes increasingly limited. Initially, they might still detect faint background radiation left over from earlier cosmic events. Over time, even this radiation becomes so stretched by expansion that its wavelength grows beyond detectability. Eventually, the sky becomes completely dark, not because light does not exist, but because it has been stretched into forms that carry no usable energy or information. The cosmic microwave background radiation, which in the current universe serves as a fossil imprint of the Big Bang, becomes almost entirely unobservable in this era. As expansion continues, its photons are stretched to such long wavelengths that they effectively blend into the background of empty space. This means that one of the most important pieces of evidence for the origin of the universe becomes inaccessible. Future observers, if they exist, may have no direct way of reconstructing the history of cosmic expansion. The structure of space itself in this era is defined by exponential expansion. Unlike earlier periods where expansion slowed or varied depending on matter density, dark energy causes space to expand at an accelerating rate. This leads to a situation where distances between unbound regions grow faster and faster over time. Even regions that were once relatively close become separated by vast stretches of empty space. In practical terms, the universe becomes divided into isolated islands of space-time, each moving away from all others. Within any given region that remains gravitationally bound, such as the remnants of a galaxy cluster before complete isolation, local physics still operates in familiar ways for a limited time. Atoms remain stable, particles interact, and gravitational systems persist. However, these regions are finite and shrinking in relative importance. As expansion continues, even these bound systems will eventually become isolated from one another, leaving only individual gravitational systems surrounded by emptiness. One of the most striking features of this era is the near absence of energy gradients. In physics, energy gradients are differences in energy that allow work to be performed. For example, stars shine because nuclear fusion creates energy differences that radiate outward. Black holes accrete matter because gravity creates energy gradients that pull material inward. In the dark energy expansion era, almost all such gradients have been exhausted. The universe approaches a state of maximum entropy, where energy is distributed as evenly as possible across space. Without energy gradients, physical processes become extremely limited. There are no stars to generate light, no black holes to consume matter, and no large-scale structures to create gravitational interactions. The universe becomes a place where change is rare and increasingly insignificant. Even quantum processes, which still occur at microscopic scales, contribute little to the overall evolution of the cosmos. Dark energy itself remains one of the deepest mysteries in physics. In this era, it is the only component of the universe that has a significant large-scale effect, yet its true nature is still unknown. Some theories suggest that it is a constant property of space-time, often modeled as a cosmological constant. Others propose that it may be dynamic, changing slowly over time as a field permeating the universe. There are even speculative ideas that dark energy could eventually decay or transform, potentially altering the ultimate fate of the cosmos. However, in the context of this era, it is typically assumed to remain constant, driving continuous expansion. If dark energy remains constant, the long-term future of the universe becomes one of endless expansion. Space will continue to stretch indefinitely, carrying all remaining particles and radiation with it. Over extremely long timescales, even the smallest remnants of matter will become increasingly separated. Eventually, interactions between particles will become so rare that the universe effectively becomes static from any local perspective. One of the most important conceptual shifts in this era is the idea that the universe is no longer defined by structure but by emptiness. In earlier eras, even in their most advanced stages, there were still structures such as galaxies, stars, and black holes. In the dark energy expansion era, these structures are gone. What remains is a vast expanse of space with extremely low density, expanding without limit. This expansion also affects the nature of time and observation. Because light has a finite speed, and because space is expanding faster than light can cross it on large scales, regions of the universe become causally disconnected. This means that events occurring in one region can never affect another region once they are separated by the expansion. Over time, each region of space becomes its own isolated causal domain, effectively its own universe in terms of observable physics. If one imagines a hypothetical observer in this era, their perception of reality would be extremely limited. They would see a dark sky with no visible galaxies or stars. They might detect faint traces of local particles or extremely redshifted radiation, but beyond that, the universe would appear empty. Without external references, their understanding of cosmology would be fundamentally constrained. They would have no way of knowing about the rich cosmic history that preceded their existence. As expansion continues, even these local particles become more diluted. Over trillions upon trillions of years, the density of matter and radiation approaches zero. Space itself becomes the dominant feature of reality, with energy playing an increasingly negligible role. The universe becomes a nearly perfect vacuum, not in the sense of absolute emptiness, but in the sense of extremely low density and minimal structure. Despite this apparent emptiness, the laws of physics continue to operate. Quantum fluctuations still occur, particle interactions still happen at extremely rare intervals, and space-time continues to expand. However, these processes are so infrequent that they have little meaningful impact on the large-scale structure of the universe. Time continues to pass, but without change, it becomes increasingly difficult to define in physical terms. One of the most profound aspects of the dark energy expansion era is its sense of inevitability. Unlike earlier transitions in cosmic history, which involved active processes such as star formation, supernova explosions, or black hole mergers, this era is defined by the absence of such events. It is not a period of transformation, but of gradual fading. The universe does not change into something radically new. Instead, it simply becomes more empty, more isolated, and more uniform. As this process continues, the universe approaches its final stages, where even the faint remnants of radiation and particles become so diluted that they effectively lose all interaction. This sets the stage for the next and final phase of cosmic evolution, the Dark Era, where the universe reaches a state of extreme isolation and near complete thermodynamic equilibrium. The dark energy expansion era is therefore a bridge between a universe filled with remnants of structure and a universe that is almost entirely devoid of meaningful physical activity. It represents the final dominance of expansion itself, where the fabric of space dictates the fate of everything within it. The universe in its most distant future becomes almost unrecognizable compared to any earlier stage of its existence. After the long dominance of dark energy and the near total disappearance of all bound structures, what remains is a cosmos that is stretched, diluted, and stripped of almost every feature that once defined it. Galaxies are gone, stars are gone, black holes have evaporated, and even the faint background radiation that once filled space has been stretched to enormous wavelengths. This is the dark era, a time when the universe is no longer shaped by energetic processes or large-scale structures, but instead exists as a thin, cold, and nearly featureless expanse of space-time. At the beginning of this era, the universe still contains traces of its earlier history. There are extremely low-energy photons left over from previous cosmic phases, particles produced during black hole evaporation, and perhaps occasional remnants of matter that have not yet been fully dispersed by cosmic expansion. However, these remnants are so widely separated that interactions between them are extraordinarily rare. The universe is effectively divided into isolated pockets of causality, each so distant from the others that no information can travel between them. To understand the dark era, one must first understand the concept of thermodynamic equilibrium on a cosmic scale. In physics, systems naturally evolve towards states of maximum entropy, where energy is evenly distributed and no gradients remain to drive change. In earlier eras, the universe was far from equilibrium. Stars created intense energy gradients, galaxies formed complex gravitational structures, and black holes concentrated mass into extreme densities. Even in the dark energy expansion era, some remnants of structure remained. But in the dark era, almost all such gradients have been exhausted. Without energy differences, physical processes become extremely limited. There are no stars to generate heat or light. There are no black holes to concentrate matter. There are no galaxies to organize large-scale structure. Instead, the universe is filled with particles and radiation that are so widely dispersed that they rarely interact. In practical terms, the universe has reached a state very close to maximum entropy, where no significant physical work can be extracted from the environment. The expansion of space continues even in this era, driven by dark energy. However, because there is so little matter left, the expansion no longer produces visible effects on structure. Instead, it simply increases the distance between already isolated particles. Over immense timescales, even the smallest remnants of matter become separated by distances so vast that their influence on one another becomes negligible. The universe becomes a vast, expanding void with almost no internal variation. One of the most striking features of the dark era is the disappearance of meaningful observation. In earlier epochs, observers could look out into space and see galaxies, stars, and cosmic structures. In this era, there is almost nothing to see. The sky would appear completely dark, not because light does not exist, but because any remaining photons have been stretched to wavelengths so long that they carry no usable energy or detectable signal. Even advanced observational tools would struggle to detect anything beyond local particle interactions. The cosmic microwave background radiation, once a key source of information about the early universe, becomes completely undetectable in practice. Its photons have been stretched so far by expansion that their energy approaches zero. They blend into the background of space-time itself, effectively becoming indistinguishable from the vacuum. This means that one of the most important observational windows into cosmic history is permanently closed. In this era, the concept of structure becomes almost meaningless. There are no galaxies, no clusters, no stars, and no black holes. Even atoms, if they still exist in isolated regions, are separated by such vast distances that they rarely interact. The universe is no longer organized into systems. Instead, it is a sparse distribution of particles embedded in an expanding fabric of space. One of the few remaining processes that continues to operate is quantum fluctuation. According to quantum field theory, even in a perfect vacuum, fields are never completely static. They undergo constant fluctuations due to the uncertainty principle. In earlier eras, these fluctuations were overshadowed by more energetic processes. In the dark era, however, they become one of the only sources of activity, although even they are extremely subtle on large scales. These fluctuations can occasionally produce virtual particles that briefly appear and then annihilate each other. However, because the universe is so dilute and cold, these events have no lasting impact on cosmic evolution. They are random, isolated, and statistically insignificant. The universe becomes a stage where quantum noise exists, but nothing meaningful emerges from it. Time in the dark era continues to pass, but its meaning becomes increasingly abstract. In earlier epochs, time was measured by change, the movement of planets, the burning of stars, the evolution of galaxies. In the dark era, change becomes so rare that time loses its usual physical significance. Without events to mark its passage, time becomes more of a parameter in equations than a lived experience of transformation. One of the most important consequences of this era is the complete isolation of causal regions. Because the universe continues to expand at an accelerating rate, regions of space become separated by distances so large that no signal traveling at the speed of light can ever cross them. Each region becomes a self-contained causal domain, unable to influence or be influenced by any other region. In effect, the universe fragments into a vast number of disconnected patches, each evolving independently. Within any given causal patch, the situation is similar. There may be a small number of remaining particles, perhaps a few photons or elementary particles drifting through space. Occasionally, these particles may interact, producing brief and insignificant events, but over time, even these interactions become less frequent. Eventually, a single causal patch may contain nothing more than a few isolated particles separated by vast empty space. As the dark era progresses further, even matter itself becomes increasingly unstable in some theoretical models. Certain hypotheses in particle physics suggest that protons, which make up atomic nuclei, may not be completely stable. If proton decay occurs, Then, over extremely long timescales, all ordinary matter would eventually disintegrate into lighter particles such as positrons, electrons, and photons. This would further accelerate the transition toward a universe dominated entirely by radiation and elementary particles. However, even without proton decay, the universe still trends toward simplicity. Gravitationally bound systems no longer exist, electromagnetic structures are rare, nuclear processes have long ceased. What remains is a universe where the fundamental forces still exist, but have very little opportunity to produce macroscopic effects. Dark energy continues to dominate the large-scale behavior of the universe. Space expands exponentially, ensuring that even the sparse remnants of matter are stretched further apart over time. This expansion is not something that can be stopped or reversed under current understanding of physics. It is a built-in property of space-time itself, and it ensures that the universe will continue to grow more empty and dilute indefinitely. In this context, the Dark Era is not a transition to a new state, but rather a continuation of increasing emptiness. There is no new structure forming, no new cycles of creation, and no return to earlier conditions. Instead, the universe moves asymptotically toward a state of complete thermal equilibrium, where all energy differences are erased and no physical processes can occur on large scales. One of the most profound aspects of this era is the disappearance of cosmological memory. In earlier eras, the universe contained structures that preserved information about its past. Galaxies recorded the history of star formation. Black holes preserved information in their mass and spin. Radiation carried imprints of early cosmic conditions. In the Dark Era, most of these records are either destroyed or diluted beyond recovery. The universe becomes increasingly uniform and uninformative about its own history. Even theoretical observers within this era would face extreme limitations in reconstructing the past. Without visible structures or energetic processes, they would have no direct evidence of galaxies, stars, or black holes. Their understanding of cosmology would be restricted to the local behavior of particles and fields within their causal patch. The broader history of the universe would be inaccessible, hidden behind the limits imposed by expansion and entropy. Despite this apparent finality, the Dark Era is not necessarily the absolute end of all possible physical processes. On extremely long timescales, rare quantum events may still occur. Some theories suggest that fluctuations in space-time could occasionally give rise to temporary structures or even entirely new regions of space. However, these events would be extraordinarily rare and would not significantly alter the overall state of the universe. In the absence of structure, energy, and interaction, the universe becomes a kind of cosmological background state. It is not active, not dynamic in any meaningful large-scale sense, but it still exists within the framework of physical law. Space continues to expand, time continues to pass, and quantum fields continue to fluctuate, but nothing organizes these processes into larger structures. The Dark Era, therefore, represents the ultimate outcome of the processes that began in the earliest moments of the universe. From the hot, dense state of the Big Bang, through the formation of particles, atoms, stars, galaxies, and black holes, The universe has moved steadily toward increasing entropy and decreasing structure. The dark era is the end point of this trajectory, where all gradients have been smoothed out and all large-scale activity has ceased. As we move toward the final chapter of this cosmic journey, we approach the most extreme state of all, the final fade. In that ultimate stage, even the faint remnants of particles and radiation become so diluted that the universe approaches a condition of near absolute emptiness, where even the concept of physical interaction becomes almost meaningless on any observable scale. In the farthest reaches of cosmic time, the universe reaches a state so dilute, so expanded, and so thermodynamically exhausted that even the faint traces of structure that once persisted in the dark era have nearly vanished. What remains is not a universe in the traditional sense of active matter and energy, but a vast, cold, and expanding space-time where particles are so widely separated that interactions become effectively impossible on any meaningful timescale. This is the final fade, the last stage in the long evolution of the cosmos, where the universe transitions from extreme emptiness into a condition that approaches absolute physical silence. To understand the final fade, it is necessary to recognize how profoundly the universe has changed since its earliest moments. At the beginning, the cosmos was hot, dense, and filled with intense energy. Particles collided constantly, forces were unified or nearly unified, and structure emerged rapidly from a primordial plasma. Over billions of years, this energy organized itself into increasingly complex systems. Atoms formed, stars ignited, galaxies assembled, and black holes shaped the largest structures. Each stage of cosmic evolution represented a new level of organization built upon the remnants of earlier processes. But every one of these stages depended on energy gradients, differences in temperature, density, and gravitational potential that allowed change and activity to occur. The final fade represents the point at which all such gradients have been smoothed out to the greatest extent allowed by physics. The universe no longer contains the conditions necessary for sustained transformation. Instead, it becomes a near-perfect equilibrium state, where entropy is maximized and usable energy is effectively exhausted. At this stage, the universe is dominated by extremely low-energy particles and radiation. Photons that once carried the light of galaxies, stars, and black holes have been stretched by cosmic expansion to wavelengths so large that their energy approaches zero. These photons still exist, but they no longer function as carriers of information in any practical sense. They are spread across an enormous and ever-expanding volume of space, so diluted that their presence is almost indistinguishable from the vacuum itself. Matter, if it still exists in any significant form, is similarly dispersed. Protons, electrons, and other particles are separated by distances so vast that the probability of interaction between them becomes extraordinarily small. Even gravitational attraction becomes negligible on local scales, because the density of matter is so low that no meaningful structures can form or persist. The universe is no longer a collection of systems, but rather a sparse distribution of isolated particles embedded in expanding space-time. One of the defining features of the final fade is the dominance of vacuum energy and the continued influence of dark energy. while matter and radiation have become negligible, dark energy remains uniform and persistent throughout space. It does not dilute with expansion, and so it gradually becomes the only component of the universe that has a measurable, large-scale effect. However, its influence is not one of creation or structure formation, but simply of continued expansion. Space keeps stretching, carrying all remaining particles farther apart, reducing the likelihood of any future interaction even further. In this environment, causality itself becomes increasingly fragmented. The universe is already divided into isolated causal regions due to the accelerated expansion that began in earlier eras. In the final fade, these regions become even more disconnected. Each region of space evolves independently, with no possibility of communication or influence between them. From a physical standpoint, the universe no longer functions as a single coherent system, but as an enormous collection of causally isolated micro-universes, each effectively cut off from all others. Within any single causal region, the situation is remarkably simple. There may be a handful of particles, perhaps a few photons or electrons, drifting through an almost perfect vacuum. Occasionally, quantum fluctuations may produce brief interactions, but these events are so rare that they do not contribute meaningfully to the overall evolution of the system. Most causal regions eventually reach a state where no further interactions occur at all. They become static in practice, even though time continues to pass. Time in the final fade becomes one of the most abstract concepts in physics. In earlier eras, time was defined by change, motion, and the evolution of structures. In the final fade, change is so rare that time loses its usual physical meaning. It continues as a parameter in the equations of physics, but there are no longer events to mark its passage. In many regions of the universe, nothing happens for durations so long that they exceed any familiar scale of understanding. Time becomes a background dimension without observable content. One of the most profound implications of this era is the near-total loss of thermodynamic activity. The universe has already been approaching maximum entropy for trillions of years, but in the final fade, this condition becomes effectively complete. All energy differences that could drive physical processes have been erased. There are no hot regions and cold regions, no dense and sparse regions in any meaningful dynamic sense, and no structures capable of performing work. The universe is thermodynamically dead in the sense that no large-scale processes can extract usable energy from it. Even quantum processes, which still occur at microscopic scales, contribute little to the overall state of the universe. Vacuum fluctuations continue, but they are random, isolated, and do not lead to sustained structure formation. Virtual particles may appear and disappear, but they do not accumulate or organize into anything stable. The universe becomes a stage where only the most minimal and local quantum events occur, with no global consequences. As expansion continues, the distances between all remaining particles grow without limit. Even photons, traveling at the speed of light, cannot bridge the expanding gaps between causal regions. Over unimaginable timescales, the wavelength of all radiation becomes so stretched that it effectively loses all energetic significance. Light no longer functions as a meaningful physical influence in most regions of space. In this condition, the concept of observation itself becomes irrelevant. There are no structures capable of functioning as observers in any meaningful sense. Even if hypothetical self-organizing systems were to arise through rare fluctuations, they would exist in an environment so devoid of energy gradients that sustaining complexity would be virtually impossible. The universe does not actively prevent complexity from forming, but it provides almost no conditions under which it could persist. One of the most important features of the final fade is that it is not a sudden transition, but an asymptotic approach. The universe does not reach absolute emptiness or complete absence of activity in a finite amount of time. Instead, it gradually approaches these conditions closer and closer as time tends toward infinity. In this sense, the final fade is more a process of endless dilution than a definitive endpoint. Dark energy ensures that this dilution continues indefinitely. Space keeps expanding, causal regions keep separating, and energy density keeps decreasing. There is no known mechanism in current physics that would reverse or halt this process on large scales. As a result, the universe is locked into a trajectory of eternal expansion toward increasing emptiness. In some speculative theoretical models, extremely rare quantum fluctuations over vast timescales could lead to the spontaneous emergence of new low-entropy regions or even entirely new universes. However, such events would be so rare that they would not significantly alter the overall state of the final fade. From a macroscopic perspective, the universe remains in a state of near-perfect equilibrium. Another important aspect of this era is the fate of information. Throughout cosmic history, information has been stored in various forms: in the arrangement of particles, the structure of galaxies, the state of black holes, and the patterns of radiation. In the final fade, most of this information becomes effectively inaccessible. Even if it is not fundamentally destroyed, it becomes so widely dispersed and diluted that it cannot be reconstructed or used in any practical way. The universe thus transitions into a state where physical law still exists, but its capacity to produce meaningful change is almost entirely exhausted. Space, time, and quantum fields continue to exist, but they operate in a regime where large-scale structure is no longer possible. The universe becomes a nearly featureless expanse governed by uniform laws but devoid of significant activity. This raises a profound philosophical implication. The final fade suggests that the universe, as a physical system, has a direction in time driven by entropy increase and expansion. From a state of extreme density and complexity, it evolves toward a state of extreme simplicity and emptiness. Yet this simplicity is not the same as nothingness. It is a state of existence where the potential for change has been minimized but not entirely eliminated. Even in this ultimate condition, the laws of physics remain. Quantum fields still fluctuate, space-time still expands, particles still exist, though widely separated and rarely interacting. The universe does not disappear. It simply becomes increasingly inactive on observable scales, approaching a condition where nothing significant happens for durations that stretch beyond comprehension. The final fade is therefore not an end in the absolute sense, but the culmination of a long process of cosmic evolution. It represents the end point of all large-scale physical activity, where the structures that once defined the universe have been reduced to isolated remnants and then to near nothingness. It is the final stage in the transformation from a hot, dense, structured cosmos into an ever-expanding, ever-thinning expanse of space-time. In the end, the universe remains, but it is no longer a universe of events, structures, or complexity. It becomes a quiet background of existence itself, stretched across infinite time, with no significant changes to mark its passage. The journey from the first moments of the Big Bang to the final fade is a story of transformation, expansion, and gradual dissolution. It is a story written in the language of physics, where the ultimate direction is toward equilibrium and the final state is one of profound and enduring stillness.